right. Hi, everybody. How are you guys? Yeah, I get that. Today, the plan is going to be we're going to do section 7.1 and 9.5. So 7.1 is integration by parts, and 9.5 is talking about another type of differential equation called a linear differential equation. Both of these topics we're going to talk about today are technically BC topics, would not appear on your AP exam, but are kind of standard Calc 2 level topics that you will encounter in your second year calculus course at university. So we're going to do them, and they're on our syllabus for the course and all that jazz. So like, that's where we're at. Everybody okay there? Okay. We're going to start by, in section 7.1, we're going to talk about integration by parts. So we've seen that we have, when we do derivatives, we have like three main derivative rules. You have chain rule, product rule, quotient rule, right? And we've seen that like U substitution pretty nicely handles the anti-differentiation process for a chain rule, right? And that'll cover some of the situations where I have like two functions multiplied to each other, but it doesn't cover all of them, right? So if I have like the wrong two things multiplied together and there's no chain ruling your way through it. So what we want to do is we want to build out some more techniques where I can handle like the product of two functions. One of these techniques is called integration by parts, where integration by parts really relies on the product rule for differentiation as its building point. So let's take a look at that. So let's say we have some function that we can think of as the product of two functions, some f of x times g of x. When I take the derivative of that, I get f of x times the derivative of g plus g times the derivative of f, right? That's just the chain rule for derivatives. Everybody cool with that? Okay. If we then like integrate both sides, that integral is going to cancel with the derivative, and we just have f of x times g of x, right? And then on the left hand or on the right hand side, then we can distribute that integral symbol through. Everybody okay there? And then we could like subtract, this integral from both sides. And we'll end up with something like this. The integral of f of x times g prime of x equals f of x times g of x minus g of x, or minus the integral of g of x times f prime of x. So that's another integration formula for the product of two functions, right? We call this formula integration by parts in the process integration by parts. And kind of traditionally, we, instead of using like f of x and g prime of x, we use u and dv. So we say that the integral of u dv is u times v minus the integral of v times du. And the hope is that when we do this process, that integral of v times du is something that we can handle with just a one of our basic antiderivative formulas, or maybe we have to use U substitution, or in the very worst cases, maybe we have to do another integration by parts. But this is the formula. Okay? So the question really becomes here, how do I choose what part of my integral to call U and what part of my integral to call dV? That's typically the hardest part. And the tip is generally we want to pick our U so that the derivative becomes simpler. And we want to pick the dV so that I have a function that's easy to integrate. So that's typically your guideline for how you're going to choose your U and your dV. Now, again, I say typically because you might run into a situation where it's maybe not obvious which one you should pick as which, or that in certain special circumstances it may be, that the U gets simpler becomes way more important than the dV being easy to integrate becomes more important than the U getting simpler kind of thing. But here we're going to just run through some examples now to get a feel for this process, and that's going to be the remainder of this lesson 7.1. It's just kind of using this process in a variety of settings. Everybody ready to roll? All right. So here we have the integral of x sine x dx. Worth noting here at the beginning, if I tried to do a U sub on this, my two candidates for U would be x and then sine x, right? If I pick U to be x, then I just end up with U sine U, and it's no different than the current problem, so that doesn't do anything for me. If I pick du to be sine x, if I take the derivative of that, I get a cosine x, and I can't make a substitution in for my du now because there's no cosine x in here either. So I'm should be pretty obvious pretty quick that a U sub isn't going to get us there. So this is a classic integration by parts problem. So I want to first start by picking the parts of x sine x dx to go into the U and the parts to go into dv. Now the dv part is always going to get the differential piece, right? So I know the dv is going to include the dx. Sometimes that might be all dv needs to be, is the dx. Now, should be probably pretty clear here that you wouldn't want to leave x sine x as the u, because if you knew how to, anyway. So probably one part of the x sine x is going to be u, the other part is going to go into the dv. So in choosing u, we want to choose u so that its derivative becomes simpler. Should u be x or should u be sine x? X, right? Because the derivative of x is 1 and it doesn't get much simpler than that. So dv then will be sine x, and that's not a problem. I can integrate sine x, no problem. That's one we have an antiderivative formula for. Everybody okay so far? I'm going to then take the derivative of u, and I find then that I can say that du is going to just equal dx. To get v, I have to integrate dv, which means that I'm going to integrate sine x dx. What is the antiderivative of sine x? Negative cosine x. So that's everything I need now to start filling in my integration by parts formula. I have u, I have dv, I have du, and I have v. So I have u times v minus the integral of v du. Everybody see where I filled everything into our formula here? Okay, and then the minus, the negative makes a plus. What's the antiderivative of cosine? Sine. And then because this is an indefinite integral, it just needs the plus c at the end. And that's all she wrote. Is everybody okay with that? Okay. If you wanted to check, you could take the derivative of that, and it should simplify all the way down to x sine x, right? Yes, Ava.
Out of the three formulas for integration backwards, are we just using the one that you starred, or can we use?
They're all equivalent.
Oh, they're all the same.
Yeah.
Okay.
So traditionally we just use the integral of u dv is equal to uv minus the integral of v du.
Okay.
That's traditionally the one that kind of everybody settles on, but they're all equivalent statements.
Thank you.
Sure. Mostly because the notation on u dv is just less writing, like it's a little more compact. All right, let's do another example. The next one is the integral of the natural log dx. So again, first thing you'd want to look at is, do I have can I do this integral using my available methods? Well, I don't have an antiderivative formula for natural log of x, right? And there's no u substitution I can do here because there's really just like one thing. So this is going to be a by parts problem. If I can't do an antiderivative formula, I can't do a u sub, then it's going to be here. I know the dx always goes in the dv, goes with dv. And there's only one other thing left, that's the natural log of x, so that's got to be my u. So that's how it has to be. There's no other way to do that, right? So if I, again, take the derivative of u, I get 1 over x. So du is going to equal 1 over x dx. And v is the integral of dv, which is the integral of dx, which is just x. And so now we have everything we need to start filling in our formula. Any questions as to what I did here? Okay, so this integral is u times v minus the integral of v du. And again, I'm just going to write the letters above, so if you're going back and looking, it's like, where are you getting this from? It's just me plugging the values into the formula, right? Now notice in our integral now, x times 1 over x is just 1, right? So the integral of dx we know is just x, and we plug the plus c on, and bada boom, bada bing. There we go at the end. I mean, could you factor some x's and stuff and write that in a snazzier way? I guess if you wanted to, but that answer is good enough for me. So far, so good. You guys ready for another? Okie dokes. All right, so the integral of t squared e to the t dt. Again, notice that if you try doing this by u substitution, it's not going to work. You'd probably pick u to be t squared, but that's not really going to work out because the du then would need to be in the exponent of the e, and that's real not. We don't integrate like that. What do you suppose we should pick as our u? T squared, probably, right? That one's getting simpler. It's going from a degree 2 to a degree 1. So that means the dv will be e to the t dt, which again is very easy to integrate, so I'm happy with that. So du would just be 2t dt, and v will just be e to the t. I cut out some work there as this is our third example. Is that okay with me cutting some of that trivial, simple derivative and integration stuff? Okay. So I'm going to have u times v minus the integral of v du. Rats. That didn't seem like that integral that's left isn't really any easier to deal with than the previous one, right? But it is a little bit simpler. Right, here we have a degree 1 instead of a degree 2 polynomial. What do you think we're going to do? Yeah, we're going to do another integration by parts. That's exactly right. So we still have this t squared e to the t and the minus, and now our new integration by parts, uv minus the integral of v. I have that 2 sitting there. Let's just put that to I guess we'll do it here. I need to put that 2 somewhere. It's probably the easier place to put it. Okay. Sorry about that. Is everybody okay with what I did? Sorry for having to go back and put that 2 someplace. Okay. And now notice the integral of e to the t dt, that's something we can handle. And there we're done. So in that example, we nested 2 integration by parts, one inside of the other. So we did one layer of integration by parts and we're left with this integral. Again, that wasn't something we could do by u substitution or had a direct antiderivative rule, so we're just going to try to do a second u substitution on that. So I picked my u and my dv. You're good with those?
Yeah.
And the results are you good with?
Yeah.
Okay. So the blue here is the result of that integral that I highlighted in yellow. We still have this piece out front. And the integral of e to the t is just e to the t. Does that feel okay? It's a lot of moving pieces there. I tried to do my best to color code things so it like, oh, I see what we're doing.
Yeah.
But, you know, we good? Okay. On to our next example. Here we have e to the x times sine x. Do either of those get simpler when we differentiate? No, right? Okay. Is one of them easier to integrate than the other? Yeah. Which one is probably easier to integrate? E to the x. So let's choose that as dv. And we'll choose sine x as u. Since, again, easy to differentiate. So du is going to be cosine x dx, and v is going to be e to the x. Is everybody okay? Okay. So apply my integration by parts formula. I have u times v minus the integral of v du. Okay. Everybody so far so good? Does it look like it helped us at all? No, right? But from the previous problem, sometimes just like another integration by parts will do the trick. So what's that? Yeah. You don't see it now, you're going to in a minute though. Let's try it. So let's do another integration by parts. Anthony's dead on that like this is just gonna like kind of be a loop here. So I don't really see why you'd want to do this other than like Mr. Kulik's trying to tell me that like apparently this loop is gonna somehow be beneficial. I'm not so sure. Oh, sorry, we didn't write. du is negative sine x dx, and v is e to the x. Should write those down. All right, oops, and then we are doing this stuff in blue. All right, so we have cosine x times e to the x. And we have minus the integral of v du okay, and let's go ahead and simplify stuff down here. Let's write that. And see if anybody sees what to do. And I have like 3 negatives. That's why this is still negative here. I'm going to zoom out a little bit because we need to see the whole thing to see it. So Anthony was saying, like, well, don't we just get like a loop? We'll get that e to the x sine x back again, right? That's what we started with. That's what we want to have happen. This is all one equation, right? So I'm just going to add that to like both sides of the equation. So I now have 2 e to the x sine x equals this stuff and now that the integration is done, because I have one side with no integrals on it, we'll put our plus c on and we just divide by 2. And we're done. I can extend the bar over the c or not. It doesn't really matter because c over 2 is still just a constant. So whether you extend the bar that divides by 2 bar over the, to cover under the c or not, it doesn't matter. Who's expecting that to happen? Nobody probably, right? So again, if you get a loop trying to do this integration by parts, that's not a bad thing. That's fine. In fact, that's helpful because then you just add over, the looped part and then you can divide by the coefficient and you're done. That was the point of that trick, or of that problem. Anthony, are you cool? You guess so? Yeah. That's not easy, right? Unless you've seen that trick, you're probably not coming up with that on your own, right? That's a nasty one. Okay. Am I free to move to the next problem here or example? Okay. Let's do one more as a definite integral problem, and then we'll move on to the next stuff. Okay, so this is an integration by parts problem as a definite integral. Now keep in mind, could you type this in your calculator and get an answer? Yup. But it's not going to be exact, right? It's going to be rounded. This one has, I don't know about nifty, but like an exact answer that we can get by doing it by hand. So let's try to do that. Now this should be pretty obvious. What's the u and the dv for this one? What does u have to be? And just, it's got to be tan inverse x, right? Because there's, the dx has to go with the dv, and there's nothing left to be u unless it's that, right? So what's the derivative of tan inverse? 1 over 1 plus x squared, and then we need the dx. And then the integral of dx is just x, right? Okay, so we have u times v minus the integral of v times du. Let's look at that integral of x times 1 over x plus 1. I'm sorry, 1 over 1 plus x squared. Can we do that integral? I can do it. It's a u sub. Yeah, what should the u be? 1 plus x squared. So du is going to be 2x dx. And we'll just divide the 2 over. And there we go. Now, this was a definite integral, right? So I should have still from 0 to 1 here. And this stuff then needs to be evaluated from 0 to 1. And I'm going to change my bounds. So I don't have to put the 1 plus x squared back in after I do my u sub. Is everybody okay how I found the new bounds for my integral being 1 and 2? I plugged 0 into x for 1 plus x squared. That gives me 1. And I plug 1 into 1 plus x squared. That gives me the 2. All right. So I have tan inverse of 1 times 1 minus tan inverse of 0 times 0 minus the integral from 1 to 2 of 1 over u, and then I'll put the 1/2 out front, du. Everybody okay? Tan inverse of 1 is pi over 4. Tan inverse of 0 is 0. The antiderivative of 1 over u is the natural log of u. We evaluate that from 0 to 1. I'm sorry, from 1 to 2. I didn't mean 0 to 1. Those were the old bounds. And then the natural log of 1 is 0. And I don't need the absolute values because the number is positive anyway. So we're done. This is the exact value. Pretty nifty. Calculator can't give me that, but it should give me an approximation. Real close. What do you guys think on this? It's not so bad as long as everything works out fairly directly. But that's the idea. So the big takeaway is you just got to have that integration by parts formula. If you have that, it usually goes pretty smoothly. Okay. On to 9.5. In 9.5, we're going to look at a new type of differential equation called a linear differential equation. So we say a first order linear differential equation is one that can be put in the form of dy over dx plus p of x times y equals q of x. When we say first order differential equation, what does first order mean? It means that the only derivatives in the equation are first derivatives. If we had a second order differential equation, then we could have second derivatives and first derivatives, and so on and so forth. Everybody okay? We won't look at any second order differential equations in this course. All right. Now keep in mind P and Q are just functions of x respectively. So let's take a look at this differential equation here. X times the derivative of y plus y is equal to 2x for x not equal to 0. So if we try to do this or try to handle this and use our techniques from 9.3 when we tried to separate the x and y's onto one side, we are not going to be able to get like some function of x times dx equal to some function of y times dy. It's not going to be able to, we're not going to be able to do that. You can try anything you want, you're not going to be able to get it to do that, which means it's not separable. So we got to find a different way. Well, if I look at this left-hand side, x times the derivative of y plus y looks a lot like that, which would be the result of a product rule derivative, right? Because what's the derivative of x with respect to x? Just 1, right? Oh, so if I make that left-hand side just the derivative of x times y, then I can just like integrate both sides. The integral will cancel the derivative. And like bada boom, bada bing, I'm like home free. Everybody's okay with that idea? Now, in this specific example, it was like tailor-made that the left-hand side just condenses down to like a product rule derivative. That won't necessarily always be the case. So what we're going to do is we want to find a function that we can multiply to both sides of this equation that guarantees the left-hand side condenses down to a product rule derivative. Similar to like when we do completing the square, we add the c term that makes a perfect square, right? Here we're going to be multiplying by some function that guarantees us that we have a product rule derivative. Everybody's okay with that plan? So the idea here is, okay, let's say we have some function that we're going to call I of x. We call that function an integrating factor. That's the name that we give for that type of function. We're not going to talk about how we find it yet. Let's just assume that we found it. And the catch is that when we multiply, or when we have I of x, when we multiply it to the left-hand side, it's going to condense down into the derivative of I of x times y. Okay, that's the property that I of x is going to have. So we have our original problem, and we multiply both sides by I of x. This side condenses down into just the derivative of I of x times y. If we integrate both sides then, the integral is going to cancel with the derivative. And then I can just divide both sides by I of x. And that's going to allow us to solve our differential equation. Okay, we'll go through and do specifics here in a minute, but I just wanted to show you that like as long as we can find that integrating factor, we should be able to solve every single time. Now for the tricky part. How do I come up with this integrating factor? Right? So here's the catch, is that I of x times the left-hand side has to give me the derivative of I of x times y. So that's what I'm going to start with. I'm going to then distribute I of x through, And I'm going to go ahead and compute that product rule, derivative. So that's going to give me I of x times y prime, p of x times I of x times y, and then we have I of x times the derivative of y plus the derivative of I of x times y. If we look, I of x times y prime is on both sides, so I can subtract that off. Everybody's good? Okay. And I now have y's on both sides, so I can divide the y off. Everybody's good. What I'm left with here is a separable differential equation. If I divide both sides by I of x, I have my function p of x on one side, and then 1 over I of x times the derivative of I of x on the other side. If we integrate both sides, we'll have the integral of p of x dx equals the integral of di over I. Well, that is just the natural log of I. And then if I do exponent base e to both sides, that cancels the natural log. And remember, if I have e to something plus c, that like e to the c becomes like my a. And there's my way to find that integrating factor I. So here's my formula. I of x is going to be e to the integral of p of x dx. That's how I'm going to choose my integrating factor. So that's going to be my first step each time. You ready to do some examples now? Okay. So my first step, it says solve the differential equation. First thing I'd want to do is to see if it's separable, because if it's separable, that's what I want to use. If you take a minute and look at this, it's clearly not, right? Then I want to check to make sure that I'm in a linear form. So I have y prime plus p of x times y equals some function q of x. We are definitely in the linear form. Everybody cool with what I've checked here initially? All right. Now let's find our integrating factor. So my integrating factor is going to be e to the integral of 3x squared dx. Everybody's good to there? What's the integral of 3x squared? X cubed. Okay. So that's what I need. I'm going to multiply that integrating factor now by both sides of my linear differential equation. Is everybody okay with what I just did? Now here's the point. This side will condense down into the derivative of I of x times y. By definition, the way we chose our I of x guarantees that happens every single time. Is everybody okay? After I've done that condensing, I can just do the derivative of both sides. The integral of both sides. The integral cancels with the derivative on the left-hand side. It'll always do that. Now, how do I do the integral on the right-hand side? Six x squared times e to the x cubed. U sub. What should my u be? X cubed. So du is going to be 3x squared dx. So when I make my u substitution, I have 2 times e to the u du. So far, so good. And then I have a plus c because my integrals are now gone. Easy to forget that. I almost did it right there. And then the last thing I do is just divide both sides by e to the x cubed. And if you want, you could simplify it down to that. Or even, I guess, if you wanted to, you could do that. To me, those three are equivalent. Let's do that again, yeah? That should probably feel a little bit of a stretch intellectually, right? Like that was not simple. Worth pointing out that this integral that you're left with here might be an integration by parts problem in the homework, since it's going to be the product of two functions, that q of x times I of x. I wouldn't expect it to be integration by parts, but I won't be surprised when it happens, because it probably will happen a couple times in the homework. Not every time, though. As we just demonstrated, we got away with a u sub this time. On to the next one. Okay. Yes. Anthony?
Did you do it? You problem with
could I do a u sub problem and do it as integration by parts? If I did the last problem as an integration by parts problem instead of a u sub. Maybe? I've never tried. I think you'd probably have to, well, you'd have to pick the u to be e to the x cubed, because you have no way of integrating that by itself. So you'd have to pick e to the x cubed to be your u, and then 6x squared to be your dv. Maybe that would work out. I'm not positive, though. I'd have to try it. Maybe at the end we can go back and circle back and give that a shot and see if it works. Is that okay? I just don't want to get too sidetracked here on a, like, what if I did this problem in the middle of this other thing that's already kind of is pretty is not easy, let's put it that way. But we'll circle back and hit that at the end. I think there should be 10 minutes or something at the end here to look at that. All right. Here it says find the solution of the initial value problem. So when it says an initial value problem, what it means is we're given this, and we're just going to be needing that to find C. So the first thing I want to check is to see if this is separable, because if it's separable, that's what I want to do. I don't want to do an integrating factor if it's not separable, because it won't work. And if I look at this for a second, I see there's going to be no way for me to attach all the y's to this dy. So I'm pretty positive it's going to be linear. The problem is, though, that it's not in the linear form right now. And I can tell right away because the derivative of y isn't by itself. So I'm going to start just by dividing everything by x squareds. And now I'm in the linear form. Everybody see the linear form? Derivative of y equal or plus my p of x is 1 over x times y equals q of x, which is 1 over x squared. So now I need my integrating factor, which is the integral, or e to the integral of 1 over x dx. What's the integral of 1 over x? Natural log absolute value of x. And notice in this problem that because x is greater than 0, I can drop the absolute value and just call that x. Everybody good with y drop the absolute value there? So I'm going to do then x times dy dx plus 1 over x times y. Oh, I'll just do equals x times 1 over x squared. This is going to guarantee me to get the integrating factor times y, or be the derivative of the integrating factor times y. And when I multiply the other side, that just simplifies down to 1 over x. Now that I've done that condensing, I can integrate both sides. The integral cancels with the derivative. The integral of 1 over x is the natural log of x. And again, I can drop the absolute values because I know that x is greater than 0 in the problem. Ugh. And when I divide both sides by x to get the y by itself, I got that guy. It's all right. Notice that at this point I would go back and plug in my values for my point here. 1 comma 2, and solve for c to get to solve for the final. I'm going to skip doing that by hand here, if everybody's okay with that. I think that's probably a pretty trivial step. Solving the differential equation is the tough part. Once you have that, though, plugging in 1 for x and 2 for y and solving for c should be pretty trivial for you guys. And I think I got one more example problem, and we are good to go. Sound okay? All right. First thing I do is I check to see if it's separable. It isn't. I want to then check to see if it's in the linear form. It is. So I'm going to find my integrating factor. Which is the e to the integral of p of x. Oops. This piece condenses down to I of x, or the derivative of I of x times y. Integrate both sides. Integral cancels the derivative. What am I going to do with this now? I don't think this is tractable, so I think what we have to do, I don't think that's going to work for anything. So we're just going to write it as this, and then we'll just divide over the e to the x squared. I don't think that'll solve by parts. I think we just have to do that and say that's as good as we can do. Let me double check the textbook and make sure that is indeed what we do here. But I don't think that's doable by parts, and it surely isn't u-subbable. Yes, that is as good as you can do. Okay. So for Sunday at midnight, or Sunday, Easter Sunday, from 7.1, we're looking for 3 through 17 odd. And then from 19.5, where you're looking through 1 through 19 odd. So that's your problem set, or the other half of your other part of your problem set for Sunday. Well, an additional problem set. Like last week, we did 9.2 and 9.3. That was also for this coming Sunday, and then we have these two for this Sunday. To finish up the semester, on the X date, we're going to work on 7.8, which is talking about improper integrals. And then our final lesson or day of lecture of the year is going to be looking at modeling. So we'll do 9.1 and 7.3, trigonometric substitution. That'll be it for this course, for content for the semester. So we basically have 2 more days of lecture, and then that'll be it for me. We'll talk when we get back from break about like test 7 and test 7 format, what we want to do with that. And after that, it's just review for the AP exam till the end of the semester. Does that sound okay for you guys? So we're looking at, like, after what we've done today, 3 sections, and that'll be it. Questions on any of that? Okay, Anthony wanted to know, we went back to this problem, could I have done this by parts? What if I didn't notice the U substitution? I tried to do this by parts. Would it work? So we had said that we would have had to pick this as my U because there is no way we can integrate e to the x cubed. Yeah, what's up? Okay. Yep. All right, so we're going to have U times V minus the integral of V du. And I don't think that's going to work, Anthony. That got worse. Right? So that gives me 6x to the 5th e to the x cubed dx. I thought for a minute we were going to get that to work out and be like, oh, we'll just add it over, and then doesn't look like it. So I don't think it's going to fly. So your answer to your question is I don't think it'll work. Unfortunately. You agree?
Yeah.
All right. How you guys feeling? You ready for spring break? You got all your bathing suits picked out? Okay. Stay out of jail.